Today we're going to learn calorimetry. Probably one of the most exciting moments of your life is about to happen right now. Okay? So, calorimetry has something to do with heat, and that comes back to this thing we all know of called the calorie. Now, tell me how to spell it. Calorie? Calorie. Okay, so calories have something to do with energy. We know that because when we talk about food or exercising or diets or whatever, everyone's counting calories and looking up calories. Well, calorie is not an SI energy unit, although it is pretty close to being one when we see where it comes from. There's other interesting heat units out there like BTUs, for instance, which is often still used in the barbecue or heating and air conditioning community. But really, the modern replacement of the calorie is the joule. The SI unit that replaces the calorie is the joule. It's a different unit, but they measure the same thing. They're units of energy. Okay. So where does this word come from? Well, caloric, historically, was what people thought that heat was made of. They thought heat was a fluid that flowed in and out of objects, and the name of this mystical fluid was caloric. Okay, or also phlogiston. I think they're kind of the same thing, but that's, I think, where that word comes from. I'm just going to double check on that. Okay, upon further checking, they are slightly different, but kind of similar. Both obsolete theories. This has to do with the fluid of heat flowing in and out of objects. In fact, flowing from hot to cold objects, as we know heat does do. Or I guess we should be careful with that. We should say that it's based on temperature, not so much heat. Heat flows from areas of high temperature to lower temperatures. Phlogiston is actually meant to be an element that gets released when something burns. So kind of related, but not exactly the same. Okay, both obsolete. But anyway, that's where the term calorie comes from this fluid that they thought was there that was behind heat. Okay, and when you think about how heat works, it's not too hard to see why people may have thought it was like a fluid. If you take a iron bar and you hold one end in a fire, pretty soon the heat will flow up the bar and you won't be able to hold on to it anymore and you'll have to drop it, right? I was just roasting weenies on the weekend, on the one day it didn't rain, and I was like thinking to myself, this is an exact example because I had a metal weenie roasting rod and I was holding it in the fire and I watched the end get like hotter and hotter and hotter. Before too long, I could sort of feel, well, it didn't get quite to my hand, but if I slid my fingers down that bar, you could definitely feel an increase in heat until you can't touch it anymore, right? You probably all have noticed this and experienced it. So it makes sense, right, in a way, that people would have thought there was like a magic fluid called caloric that flowed in and out of objects. Not too surprising. So what is a calorie? So the calorie is defined. Definition of a calorie is the amount of energy required to heat a gram of water 1 degree Celsius. Okay. So we learned about specific heat before. So the specific heat of water in terms of calories is 1, right? So it's 1. Now what units is that? Well, that is 1 calorie per gram per degree Celsius. Oops, that backwards. Okay. So that is not used anymore. Basically, it's an energy unit based on water itself. And you might think like, okay, so why isn't that the SI unit, right? Like when you think about where our other weights and measures come from, you know, if you remember back, the meter comes from the distance between the equator and the North Pole, and it's 1/10 millionth of that distance. Then if you take a cubic meter and you fill a cubic meter with water, that weighs 1,000 kilograms, right? 1/1000th of a kilogram is your gram that you're talking about here, and the amount of energy to raise that 1 degree is the calorie. Why do you think that maybe that's not the best way to define a unit of energy for the SI unit? What might be an issue with that? Ah, okay, right. There is some other stuff going on there. You're right. You have to define the conditions that this happens under, right? Um, so what sorts of things can affect how much energy it takes to, heat water? One thing could be the pressure that it's happening at, right? We've probably seen from our experience where, a teacher might put a beaker of water into a vacuum pump, reduce the pressure enough that the water will start to boil at room temperature. And if you've never seen that before, we can do a little demo of that, if you remind me, and we can actually make water boil at room temperature, right? Because boiling is actually an equilibrium between exterior pressure on the surface of the liquid and interior outward pressure that, the kinetic energy of the particles, I guess, is exerting upward and outward on that liquid. So if you reduce this pressure enough, boiling can start to happen right inside the liquid. So pressure probably does play a role in how much energy it requires. So you have to define this value, right? And the other thing is this value changes depending on temperature, okay? So the amount of energy to go between, say, like, 0 and 1 degree is different slightly than to go from, say, 4 to 5 or from, 98 to 99. That changes slightly, okay? To be honest, I don't know enough to know exactly how it changes, but if somebody is interested in doing a project on that or a design lab, we don't call them design labs anymore, but that would be an interesting one to check out. How does the amount of energy required to heat 1 gram of water 1 degree change with temperature? Okay, anyway, so there's kind of, I guess, issues with this. You have to be very specific about where and when it happens, whereas the modern definition of energy, the joule, is pretty straightforward, right? Do you remember what it is? How do we define the joule again? Right, it's a Newton meter. So in other words, it's applying a force over a distance. Okay? And that really shouldn't change. You shouldn't have to define conditions for that, right? You do a 1 Newton force for 1 meter and you've expended 1 joule. Okay? So in terms of joules, how do we convert between the two? Well, 1 calorie is equal to 4.186 joules. Okay, so the specific heat of water in terms of joules is just that number. So in other words, you got to put in 4.186 joules of heat energy for every gram to raise it a degree Celsius. And note, just a side note, the size of the degree Celsius is the same as the size of the degree Kelvin. So you may see it, I shouldn't say the degree Kelvin, it's just Kelvin, okay? The size of the degree, though, is the same in either one, so you can essentially use this interchangeably. But, so, yeah, just one thing to note is that this value also changes with temperature. This is somewhere in the ballpark of around room temperature. So water at room temperature requires this amount. Water's most dense at 4 degrees. This value is slightly higher around there. And it actually goes a little bit lower as you get hotter and then gets higher again. I mean, it's fairly minuscule. This is a nice average that you can kind of just use. I think it's probably safe to say, up to this digit we're good, but beyond there, you got to watch. Oops. Okay. I'm gonna stop right there. 2 is